It strikes me when we look back at real scientific progress, the path isn't usually straight, is it? It's often more like a long, winding road.
Yeah, definitely not a sprint. Someone even said achieving consensus in research can be extraordinarily arduous.
That phrase really stuck with me, and it kind of sets the scene perfectly for what we're digging into today.
Absolutely. We're looking at the Alberta Plan for AI research. It's this really forward-looking piece by Richard Sutton, Michael Bowling, and Patrick Pilarski, from the University of Alberta and DeepMind.
Right.
And this isn't about like the AI generating images or the latest chatbot everyone's talking about. It's much more fundamental. It's their long-term vision for, well, creating genuinely intelligent systems.
Okay, so for you listening, if you want to get a sense of where AI research might actually be heading, like beyond the current hype, this Alberta Plan is kind of like a roadmap, right?
Yeah, it tries to cut through the noise and focus on the really big questions. How do we actually build minds, computational minds, that can learn and adapt in truly complex ways?
So less about immediate apps, more about the foundations for future breakthroughs, the kind that could really change things, economy, society, our lives.
That's the idea. And our mission here is really to pull out the core ideas of this plan for you. We're zeroing in on their main vision and this pretty ambitious research path they've laid out for, say, the next 5 to 10 years.
And important to stress again, this isn't about selling products tomorrow.
Not at all. It's about the deep scientific understanding they believe we need first before we can really make the next big leaps.
Okay, let's jump into that core vision then. What's the central idea? Like, what's it all based on?
Well, at its heart, the Alberta Plan sees intelligence as basically a process of signal processing over time.
Signal processing.
Yeah, think of an agent, an AI system interacting constantly with its environment, right? It gets sensory input, and its main job is to learn how to predict and eventually control those signals. And there's one signal that's super important: reward.
Ah, the reward signal. That tells it if it's doing well.
Precisely. It's built on the standard reinforcement learning framework. You've got the agent, the environment, actions, observations, and that key reward signal.
Right.
And a key point here is that the observation the agent gets, it might not tell it everything about the environment's state. It's often working with, incomplete information.
Like us in the real world, basically. We never have the full picture.
Exactly. Now, they highlight a few things that make their approach distinct. The first one is this emphasis on ordinary experience.
Ordinary experience. What does that boil down to?
It means they believe AI should learn primarily from its own interactions, its observations, the actions it takes, the rewards it gets.
So not relying so much on, say, massive data sets labeled by humans or constant guidance.
Right. It's different from approaches that lean heavily on pre-labeled data or lots of human help or giving the AI tons of built-in knowledge.
It's more about learning by doing then, just figuring it out through interaction.
That's the core of it, and it links to something they call the bitter lesson from AI history.
The bitter lesson. Sounds intriguing.
Yeah, the idea is that methods that really scale well with more computing power, which basically means learning and search, have historically won out in the long run. They often outperform approaches that rely more on human insights or carefully engineered knowledge.
So the bet is on methods that get better the more computational muscle you throw at them.
Kind of, yeah. They argue that truly general, scalable AI will come from agents learning mostly from raw experience.
Interesting. Okay, that's the first distinguishing feature. What about the second one? Temporal uniformity.
Temporal uniformity basically means treating all moments in time equally.
How so?
Well, the learning algorithms don't have like separate training modes versus performance modes. There's no special period where rewards are counted differently. Learning, planning, even building its understanding of the world, it all happens continuously at every single time step.
Ah, okay. So it's not like learn for a while, then stop learning and just act. It's always learning.
Always learning, always updating. This naturally leads them to focus on environments that are always changing, non-stationary environments, and on concepts like continual learning and meta-learning.
Meta-learning being learning how to learn better.
Exactly. Now, they do admit sometimes you might want to break this rule temporarily for specific reason. But they see that as a conscious choice to step away from the main principle, not the default.
Okay, got it. The third feature is being aware of computational considerations. Sounds pretty crucial.
Absolutely. Moore's law keeps giving us more computing power, but it's still finite, right? So the plan stresses that AI methods must be able to effectively use this growing power. Scalability is key.
Right, methods that actually benefit from faster hardware. It ties back to that bitter lesson again, doesn't it?
It does. Methods that scale with computation are favored. And practically speaking, these limits affect decision-making. There's a trade-off. React super fast or take a bit more time to compute a potentially better plan.
Yeah, the quick reaction versus careful thought dilemma.
Right. And the plan leans towards uniform time steps.
Yeah.
A quick reaction isn't always the best, but sometimes it's necessary. But importantly, they say being reactive doesn't rule out planning. The agent can take immediate action while also thinking ahead, refining its strategy over time.
Okay, that makes sense. And the fourth feature, something about other agents.
Yes, the focus on multi-agent environments. The plan explicitly includes scenarios where the environment has other intelligent agents in it.
Humans or other AIs.
Could be either. This opens up research into communication, cooperation, competition, how AIs learn to interact intelligently with others.
Okay.
And related to this is the idea of intelligence amplification, or IA.
IA, intelligence amplification.
Yeah, the idea that one agent, AI or human, can enhance the capabilities of another agent. They actually cite some foundational work here from people like Ashby, Licklider, and Engelbart.
So it's not just making standalone smart AIs, but also AI that helps us or helps other AIs become smarter or more capable?
That's exactly it. Understanding how an agent can use its learning to boost another agent's perception, action, or thinking. It's like a force multiplier for intelligence.
Okay, so let's try and wrap up this core vision. The Alberta Plan sees AI as maximizing rewards online through continuous sensing and acting with limited computation, possibly alongside other agents.
That's a great summary. And they themselves say it sounds almost classical, but it's also a bit contrarian compared to some trends.
How so?
Well, a lot of research focuses on offline learning from static data sets, right? Less emphasis on this continuous real-time interaction and learning from direct experience. They're pushing for a return to some core ideas, but with this huge emphasis on scalability and learning from scratch, essentially.
Right. It's a compelling vision. So how do they propose actually doing this? What about this research roadmap?
Okay, yeah, the roadmap. It's laid out in 12 steps. They progress from like fundamental algorithms up to complete prototype AI systems.
12 steps. Sounds methodical.
It is, but they also stress it's not strictly sequential. It's more like a parallel effort. They talk about developing the individual components, the chickens, at the same time as integrating them into working systems, the eggs.
Chickens and eggs, okay. You need the parts, but you also need to see how they fit together.
Exactly. You can't build the car without the engine, but figuring out how the engine fits might change how you design the chassis, you know.
Makes sense. So what are some of the early steps?
Well, the first few really focus on building the basics. Representation, prediction, control. Step 1 is representation I. Continual supervised learning with given features.
Okay, break that down.
So here the challenge is getting learning to be fast, stable, and efficient over long periods, and how that learning helps the AI represent information better, even when it's starting with a fixed set of basic inputs or features.
So mastering the tools it has before inventing new ones.
That's a good way to think about it. They're looking at improving standard methods like stochastic gradient descent, maybe by auto-tuning learning rates for different features or normalizing features, all within this continual evolving data stream.
Okay. Then step 2 is representation 2, supervised feature finding. So now it does start inventing.
Exactly. Now the focus shifts to how the AI can actually create new, hopefully better features by combining existing ones. And this is happening continually, maybe while it's facing different tasks one after another.
That sounds complex.
It introduces a big challenge, resource management. The AI only has so much computational power. How does it decide which new feature combinations are worth exploring? How does it figure out if they're useful? And when does it ditch old features that aren't pulling their weight anymore?
Right. It's like deciding which tools to keep in your toolbox.
Pretty much. Constant experimentation and refinement. Keep what works, try new things.
Okay. What's step 3?
Step 3 is prediction I, continual GVF prediction learning, GVF.
Generalized value functions. Basically, it takes the representation ideas from steps 1 and 2 and applies them to predicting things from sequential, real-time data, the kind of data the agent gets from interacting with the world.
So not just predicting one overall outcome, but maybe lots of different things about the environment simultaneously.
Exactly. GVFs let it build a richer understanding. They want to predict many signals of interest. And a key goal here is achieving what's called off-policy learning in real time, possibly using recurrent networks. Off-policy learning. That's learning from observing, not just from doing.
Yeah, like learning to cook by watching a cooking show, not just by trying recipes yourself. It lets you learn more broadly.
Got it. And step 4, control I, continual actor-critic control. Now we're getting to action.
Yes. Now we apply all those learning principles to actually controlling things, making decisions. They start with simpler problems like multi-armed bandits.
Like choosing which slot machine lever to pull.
Kind of, yeah. Then they move to more complex sequential tasks. The agent needs to learn a policy, the actor part, that chooses actions, and also how to evaluate those actions, the critic part. And it has to do this continually and reliably, even while it's still figuring out what features are useful.
Okay, so these first 4 steps build a solid foundation. Representing, predicting, acting, all continually. Where does it go from there?
Well, steps 5 and 6 extend these ideas to handle tasks that don't have clear endpoints, focusing on maximizing reward over the long haul in ongoing scenarios. Then step 7, planning I, starts to bring in internal models of the world and planning into this continuous framework.
Okay, models and planning. That feels like a big step up.
It is, and that leads directly into step 8. Prototype AI. One-step model-based RL with continual function approximation. This sounds like their first integrated system.
Prototype AI, the first real egg.
You can say that. It aims to combine average reward reinforcement learning, an internal world model, planning, using that model, and this continual function approximation capability we've been talking about.
But it's still one step. What does that limit?
It means the model and planning are focused on the very immediate future, just the next step. It doesn't yet handle reasoning or planning over longer time horizons. What we call temporal abstraction isn't really there yet.
So it's an AI that can learn, build a very short-term model, and plan just its immediate next move.
Pretty much. They expect that just integrating these pieces, even with the one-step limit, will be challenging. It needs to constantly update its perception, maintain its model, find good features informed by the model, rank those features, control its search or planning process. Lots of moving parts.
Okay. Then step 9 is planning 2, search control and exploration, refining the thinking process.
Exactly. This focuses specifically on how the AI manages its planning. If planning is like updating values in its internal model, the order in which it does those updates matters a lot for efficiency.
Like searching smart, not just hard.
Right. They look at techniques like prioritize sweeping focusing updates, where they'll make the most difference, maybe even bringing in things like Monte Carlo tree search, which is used in game AI like AlphaGo. It's about making the internal thinking more effective.
And then we hit step 10, prototype AI 2, the stomp progression. Stomp. Sounds serious.
It stands for subtask, option, model, planning. This is where they really tackle temporal abstraction, letting the AI think and act over longer timescales.
How does stomp work?
The idea is to take the useful features the AI has learned and use them to define subtasks like mini-goals. Then it learns options, which are essentially skills or mini-policies for achieving those subtasks.
Like learning to open door as a skill.
Exactly. Then for each option or skill, it learns a model of what happens when it uses that skill. And finally, these skill models get integrated into the overall planning process, so it can plan using these higher-level actions, not just primitive movements. Figure 3 in their paper shows this visually.
So it's building complex behavior by combining simpler learned skills, like building sentences from words.
That's a great analogy. And critically, learning these options and models needs to be off-policy, so it can learn about skills even when it's not currently using them.
Very cool. Then step 11, prototype AI 3, Oak. Sounds like another level up.
Oak is envisioned as even more advanced. It builds on prototype 2, but adds a crucial capability, continuously evaluating and potentially replacing any of its internal components.
Replacing what?
Features, subtasks, options, models, basically anything. If a skill or a way of seeing the world isn't proving useful anymore, Oak should be able to figure that out and swap it for something potentially better, maybe based on a less used feature it hasn't fully explored.
So it's constantly self-optimizing, pruning and refining itself.
That's the goal, continual improvement of both its state abstraction, how it sees the world, and its time abstraction, how it acts over time. They also mention an option keyboard idea here.
Option keyboard.
Yeah, where learned skills are linked to subtasks, and the AI might activate multiple skills at once, like playing a chord, to achieve more complex goals. They have a couple of ideas about how that might work.
Fascinating. Okay, and the final step, step 12. Prototype IA, intelligence amplification. Back to IA.
Exactly. This step is about demonstrating how a prototype AI2 agent could actually enhance the abilities of another agent, human or AI.
How would that work?
They imagine two ways. One is like a computational exocerebellum helping the other agent mainly with prediction and building useful features or perceptions. The other is a computational exocortex, influencing the other agent's policy or planning, boosting its intelligence more directly.
So AI as a cognitive enhancement tool.
Precisely. They plan to study this in both human AI teams and AI teams, and they mentioned some early work already exploring this.
Wow, that is quite a roadmap. It's incredibly ambitious. So if we had to boil it down, what are the absolute key takeaways from the Alberta Plan?
I think the big things are this relentless long-term focus on understanding the fundamentals of intelligence, not just short-term gains. Then, the strong conviction about learning from ordinary raw experience. Third, this principle of temporal uniformity guiding the algorithms. And finally, the absolute necessity of scalability methods that thrive with more computation.
And the roadmap itself, while maybe flexible, gives a concrete direction.
Yeah, it's a clear, if challenging, path towards their vision of truly intelligent agents.
Thinking about this emphasis on continuous learning, continuous adaptation, it really makes you wonder, doesn't it? How might AIs built this way actually change our definition of what intelligence even is?
That's a huge question, right? And tying into that with the focus on intelligence amplification, what kinds of human AI collaboration could become possible? Things we maybe can't even properly imagine right now, perhaps even in the next, say, 10 years.
It definitely points towards a future that could be very different, a long road ahead, but a fascinating one.
Absolutely. And for you listening, if this has sparked your interest, definitely look up the paper, The Alberta Plan for AI Research. Goes into much more detail.
And the researchers are quite open about wanting others to join this pursuit, right?
They are. It's framed as a broad scientific quest to understand and build intelligence, a really ambitious long-term goal.